excited to hear your talk. It's 6 p.m. here, and
okay.
your talk is 35 minutes with questions. So at about say the 27-minute mark, I'll give you a heads up.
Okay, great. Thank you.
Please go ahead.
Yes.
Share screen.
Great. Thank you. Thank you very much for the invitation. I'm sorry I can't come. I got just really busy in September, but it's great that I can do it in Zoom and present this work. Let me share my screen and we can get started. Okay? Oh, come on. Oh, God. There we go. Screen share, slideshow. Do you see my screen now?
Yeah, it looks fine. Please.
Okay, great. Okay, today I want to talk about the importance of noise in NISQ, near-term intermediate-scale quantum computers. And obviously noise is very important on near-scale quantum computers. I mean, we're at this point, used to abstracting away the concept of a qubit, which of course is a very useful concept and allows us to think about quantum computation in a very powerful way. But of course, that's only an abstraction. We're dealing with real hardware. And especially in the near term, especially right now, before we have error-corrected quantum computers, this is a fundamental constraint on what we can do. So today I want to talk about, the power of quantum computation, simulation, and noise, put some constraints on that, and then a little bit about noise metrology and methodology and how we should be thinking about it. I do want to admit that I come from a background where noise is very important. I was part of the John Clark lab, and where noise is the signal, if you can kind of think of it that way. So, this is definitely something I've always thought about in my career, but I think it's important to really think about this as we think about these quantum systems. Okay, so why do we measure and specify noise? And I'm just going to make the statement that as people talk about near-term quantum computers, what I find is when I go to talks and conferences, the majority of talks don't really discuss noise. They abstract away the qubits, do interesting things, but they're not talking about noise too much. And I think it's just important to do that. Now, there's good reasons to do that. The physics is interesting in itself. The abstraction is very useful. For example, you're looking at phase transitions of a quantum simulator or something. You don't necessarily need to know the noise about that. It's maybe robust, the noise. But we certainly publish nice papers and do something new if we're doing that. But to really explain why I think noise is very important is in physics experiments, you traditionally have to discuss the errors to reproduce, to understand the limits of your measurements. So it's an important part of what we're doing. We're building computational devices, and noise do matter. We really want to know, with these computations, are we doing actually something powerful? We're building programmable quantum computers. How well do we know the programming, the parameters of that? We want to do error correction and totally abstract away the qubits. That's limited by noise. And then finally, this is almost the most important thing. To make progress in this field, my thesis, and I'll talk about that, is we have to improve quantum computers, make the qubits better. And I think if you talk about noise, then students will, postdocs, young people, will see that's important, and thus will fix the problem, okay? We have to be realistic about this. So I really wanted to talk about noise to motivate people to think about it more carefully, solve the problems, make our qubits better. Okay, let's first start with approximate solutions to quantum computation. I'm sorry I don't have a good reference here, but there's been a lot of work on efficient simulation of qubits with quantum tensor networks. And the basic idea is you can do very efficient classical computer simulation of quantum systems using tensor network approximations, but it introduces errors to the calculation at about a couple % or so level, at very qualitative. And my conjecture here is that there's a near-term NISQ threshold conjecture, it's a conjecture, that quantum computers and simulators thus can be efficiently simulated with errors for a few %. And if you want to do something valuable that you can't do with a classical computer, your hardware should ideally be below this threshold. So, a corollary to this is saying some kind of quantum advantage from your quantum computer can't really be claimed without error measurement and showing that your errors are, better than this number. So it's approximate. I'm not quite sure it's true all the time, but one should be aware that our quantum computers are competing against very powerful classical computers and algorithms. And of course, classical computation methods are getting much better over time, so it's, it's really kind of pushing us to get our errors below a few %. Okay. Now, the second thing I'd like to talk about is you want to build these quantum systems to prove quantum supremacy, quantum advantage, or do something better than you can do classically. And it's actually kind of hard to prove that, hard to show that. How complete is the classical simulation theory? Have you tried all the best methods? And maybe you can use some more approximation methods to give semi-qualitative or even quantitative answers to so it's kind of hard. Basically, you're trying to prove a negative here, which is hard to do. And I'm also going to say, psychologically, you do an experiment. You try to reproduce it with some classical methods to see this. There's not a lot of motivation to show that you can do a classical simulation because then you're going to negate the value of your experiment. So one has to be very careful to do that. Now, some algorithms can be proved difficult, so it is possible to do that, but it's actually kind of hard to show that the quantum computer is really showing some quantum advantage to it. So, okay, so let's go on. We'll go on to the next thing. So one of the things I want to talk about is it turns out that it's very powerful just to talk about the errors in your quantum computer using classical error probabilities. You do a logic gate and you say there's a certain probability of an error, and you say it can be either a bit fit or face fit. It can be a depolarizing error with no particular direction to it. This is kind of funny because quantum computation is with amplitudes, and you formally need quantum tomography to talk about it very carefully, and sometimes that's very useful. But I really want to argue here and later on in my talk that although error probabilities is kind of a simplification, it's nice because it's simple and easy to understand. You can measure and predict it, especially for a large system, what the system performance is. Now, it's only a first-order estimate, but it's still useful to do that. And what I would say is, it's not been done too much in the field. We've done it in the quantum supremacy experiment, but I think if more systems were to use this classical error probability idea to measure and predict the fidelity of very difficult algorithms, large algorithms with this, I think that would be useful. And by the way, there's reasons why error probability is not a bad concept to do. First of all, you can have algorithms where you basically randomize the states using randomized compiling. It's just a gauge transformation. You're solving the same problem, but by doing this kind of spin echo or dynamical decoupling with your algorithm, you actually justify using probabilities. And actually, this makes your algorithms more stable in terms of mitigating certain errors. And we'll talk a little bit about the quantum supremacy experiment, showing that this is not a bad approximation. So one of my points here is we need more experiments to test the validity of our algorithms, what should be the expected fidelity. We need to check system fidelity, and you know, error probabilities are actually a good way to do that. I want to talk a little bit next about where we are as a field and talk about why this is such an important concept. And I want to first give an analogy of errors in classical computation. So on the left, I give an example of an adder using classical logic circuits, say made out of CMOS. And the point I want to make here is the size of the logic circuit we can build basically go as 1 over the error in the logic. So if you think back to the 1960s, you could do fabrication where you would get a transistor error, fabrication error, it may be 1 in 100 or 1,000 transistors, and you could build modest-sized TTL circuits and build up a classical computer from that. In the 2020s, we have fabrication where the error rates are maybe 1 error in 10 to the 10, 10 to the 11 transistors. So you can build enormous processors with 10 to the 10, 10, 11 logic gates and get them to work. And mitigating or reducing errors are absolutely key in the CMOS space to get this to work on. So similarly, errors in quantum are very important. Now, quantum is a little bit different because instead of laying out a circuit in space, you kind of lay it out in time, where you have qubits, say here W qubits, and then over time, step 1, you do a certain amount of operation, and step 2, you do more operations, and you program it, just kind of like how you would program a regular computer. So it's laid out in time instead of space, but it's a similar concept. Now let's just ignore fabrication errors for now, because the real source of the errors for what we're looking at right now is the intrinsic errors of the quantum gates of the systems. And if you have in time a depth d of number of instructions that you do, the total number of operations is the number of qubits w times the depth d, and that's going to be 1 over the error of the gate. And that wd is more or less, simply the clearance time over the gate time. Now, if you just plug in numbers, where are we right now in the field? You have a width of 100, people are talking about these kind of systems to build. You have an error, it's about 10 to the minus 2, that's typical. And you plug that into these numbers, and that means you can have a depth of 1. 1 instruction set. Now maybe you do error negation and other things, maybe it's 3 or 5. But what can you do with 3 or 5 instructions? Can't do much. This is a problem, okay? So we have to fix this, and you fix it by getting your errors down. And if you get 10 minus 4 errors, then you can do a decent, large enough size to do something powerful. You do a depth of 100, you can run real algorithms, okay? So it's really important to improve qubits. That's the message. You have to lower the noise. Now, just to be really clear about where we are here, here's some data from the Rigetti SPAC back in the beginning of the year. Things have improved since then, but this is pretty typical here. So you see that the errors of these various systems are between 1% and 2%. Google's a little bit lower. That's why we were able to do the quantum supremacy experiment. But even a 1% error might be overestimating estimating, or, being a little bit generous about where errors are. Beware, as you look in the literature, there's what I would call lots of fake news, okay, where people quote test results, they say 2 good errors on only 2 qubits, not a big system. It's hard to get low errors in a big system. So it's a big problem. We have to, we have to fix this. We have to make our errors lower, either both for NISQ, as I just described, or if we want to do error correction, we really need to get that at least to 10 to the minus 3. So there's a big need to do this. Okay, so let's talk a little bit now about the strategy for measuring and checking errors. And I'm going to call this, it's one way to do it, there's many ways to do it, but for me this is kind of an example of a gold standard of doing things really carefully in a way that you really understand what's going on. Now, you can start out by doing single qubit gate tomography or 2 qubit gate tomography. You can see that on the right. Start off in a known state. You do some, you have some unitary in the center, and you change the measurement axis and the initialization axis to figure out what goes on with the gate. And this is great. It tells you if the gate's working right. You want to understand that. However, because you have errors in the state preparation and measurement, it's hard to pull out that. But more importantly, when you build qubits and you abstract away in a circuit model, I do this gate and then this gate and this gate versus time and versus qubits, that's an abstraction. In a real quantum computer, you have crosstalk, both in time. One gate can affect another gate in the same qubit over time, or one gate of one qubit can affect another qubit. And you have to understand if you're getting crosstalk errors. Now, one of the nice things you can do is you can do randomized benchmarking or cross-entropy benchmarking to see what happens to the performance of your gates as you do it over and over in time, and you can see if things will degrade. So what you do is you take the gate you want to measure, and then you put randomized single qubit gates over time, and then you know from calculations what answers you should get, and you compare that with what you measure with your system. And you can change the number of cycles here and see how the fidelity of the final answer changes with the number of cycles, and then get an average error per cycle. And then you can compare that to what you expected from tomography or from T1, T2 kind of measurements and see if things are getting worse in some way. Okay, so that tells you about time crosstalk. Will one gate affect another gate? But you want to know if one qubit will affect another qubit. So what you then, of course, do is you're building bigger processors. And then what you do is you run these kind of single and 2 qubit randomized benchmarking, or XEB, on individual qubits in your big array. And that way you know if there's crosstalk in space, and you understand that. And then, of course, you want to run a big algorithm in the end. And then you want to figure out, when you run all these qubits, they're all operating at the same time in space and time, you want to know what your fidelity is. And of course, you measure that in all these different levels, and you compare, and you can see if the error probabilities are giving you sensible answers. And you have to do this. You can't depend on your abstraction, this theoretical abstraction. You have to measure whether the qubits are working right, because, nature is conspiring against you, okay, to make it work right. Okay, so that's the basic idea. And just to go into a little bit more detail here, quantum state and process tomography, again, like I said last time, it's most fundamental. You can understand the full nature of the gate and maybe fix problems with it. It's hard to separate out state preparation and measurement errors, and then it scales backwards. So it's good for an initial check. But people have been doing randomized benchmarking But the problem with the standard randomized benchmarking is you're comparing the results to Clifford gates, okay? You're building an analog system, okay? And a Clifford gate is a specific gate, and you're never going to hit that exactly. And okay, you can see how close you got to the Cliffords. One of the things we did when we did the quantum supremacy experiment at Google is we used cross-entropy benchmarking, which is very similar to randomized benchmarking, but you can benchmark against an arbitrary gate. And basically what you do is you run these arbitrary gates, and then you adjust your simulated model in the computer, and you adjust the parameters till you get the best fit to the data that you get out of it. And that way, you know the full unitary of the gate that you're testing. So you know for a 2-qubit gate, you know the various rotation angles and all that. You can figure that all out. And it gives you the best fit plus an average noise. And that's actually what you want to know. You don't want to be not necessarily interested to know how close you are to Clifford gate. You want to know, what is this gate that you made, the errors of it. And then once you know the gate, you can then adjust your control system to match that to, say, a Clifford gate that you want to build. So it's a nice sequence to know exactly what you got and then to optimize. Now in XEB, this works up to 30 to 50 qubits, where you can still calculate, maybe a little bit more. That's good enough to really test a big patch of it. There's other methods too that you can test for even bigger systems. But I really like this because you can measure what you made. Okay, so let's talk about the quantum supremacy experiment where we actually did all of this. What I'm going to talk about first is we have this big 53 qubit array. And the first thing you do is take single qubit gates and you measure them one at a time, separate experiments, where we turn off the couplers, we detune the qubits, we know what's going on. So you do the randomized benchmarking over the whole system, you get a more or less a Gaussian distribution. We like plotting that as an integrated histogram, you don't lose any resolution, and you get this dotted line. And it's the average error is about 0.16%. Now, when you operate a quantum computer, you're not operating all the gates separately, you're operating them at the same time. So we then just turn off the couplers in our device, measure the single qubit gates all at the same time, which of course is more efficient. It's 53 times faster. And then we get a randomized benchmarking error, and that's given in the black line here. And of course, when you do it simultaneous, it's going to be a little bit worse, but the good news is it's not that much worse, just a tiny bit, 0.15 or 0.16. So that's good. We understand what's going on. Now you can do the same thing with the 2-qubit gates. You do pairs of gates, turn everything else off, you measure that. When you do the pairs of gates, you need to subtract away what the single qubit errors were to help understand that. And that's given by this E2 dotted line right here. And it's 0.36% error on average. Now note, because it's 2 qubits, you expect the error to be larger, more or less, roughly a factor of 2. And that's kind of what we see. It was 0.15, it maybe should have been 0.3%, maybe a little lower, but it's close to that. So yeah, I think the gates are working kind of well. But that's a check. Okay, you could do a check to see if it's okay. And clearly we could improve that. The bigger issue is then when you start doing simultaneously, you run these 2 gates and these 2 gates and these 2 gates at the same time, you then get that data, and then that's the solid green line, and you went from 0.36% to 0.62%. That factor of 2, that's a factor of 2, that factor of 2. That's not good. That's saying that there is some crosstalk and your qubits are interacting with each other in some bad way. And that tells you you have to fix something, okay? And I think over time the group has been fixing that and making it better. But just comparing these random these probabilities tells you that you have to fix it. Now, it doesn't tell you exactly what to fix, and there's other ways to do that, but it does tell you what you need to do. Finally, what you want to do is you're going to run a big complex algorithm, and you want to know what the fidelities are to be then, okay? And that's what the quantum supremacy, in fact, was about, is comparing these simultaneous errors, given here, which are still single and 2-qubit gates, to the whole system. And you want to know, do things get really bad? And given that, when going to simultaneous, the gates got worse, that's something you want to worry about, okay? You don't know how it's going to work. So the validation algorithm for quantum supremacy is basically, you run this circuit here with known but randomized gates, and that basically gives you an output where you see all the possible states, but because of the coherence of the algorithm, some states are going to be more probable than others, just like when you have laser light going through a diffuser, some directions of the light scattering will be brighter than others. So you basically see qubit spectrum. And what you do in the cross-entropy benchmarking is you're basically you're measuring the brightest states, the most probable states, and you're then doing a computation of your circuit and checking whether the states that you're measuring are actually the brightest states. And you do that using this cross-entropy benchmarking, where for the states we measure, you take the probability that you computed. And if it's randomly, this p is going to be 1 over 2 to the n, and fidelity 0. And then if you measure the brighter states, the probability is a little bit higher than 1 over 2 to the n. And when you work out the theory for the Porter-Thomas distribution, it's going to be equal 1. So if it's 1, if it's a perfect match, 0. If there's any error, there's a bit flip, there's a phase flip, this fidelity goes to 0. In fact, by noting how close to 0 or 1 it is, you can measure the probability that you have no bit flips or phase flips for the entire algorithm. So this is a really good way to check whether things are working right. So that's what the quantum supremacy experiment is about. Here's the data. The red circles are the results of the quantum supremacy experiment. Here at 12 qubits, it's about 250 gates total. The fidelity is about 40%. And then as you make it bigger and bigger, of course, there's more errors, and the fidelity is going to drop. And at 53 qubits, it's about 1% or so, statistically significant than 0. And in the beginning, it's kind of a laptop, and then a workstation, and then kind of data center at the largest value. Now, the thing that I really want to focus on here is this black line here, and that's the prediction from the 1 and 2 qubit measurement errors, which really agree quite well with the cross-entropy benchmarking. And this is what's important. And let me go on to the next slide and say the probability prediction for the system fidelity is just the individual fidelity of every single qubit gate, 2 qubit gate, through the whole array, the whole time, and then of course the measurement probability at the end. And what you saw is that the predicted system fidelity is what we had predicted from the single and 2 qubit errors and the measurement errors. So this is really good. It says there's no additional decoherence physics that's coming about when we're building a big system. And this is not obvious that'll happen. And I hear anecdotal evidence that other quantum computers that people are building that's not happening. And there's reason this is working so well in terms of experimental design. It means that error corrections have worked. This is one of the fundamental assumptions you make in doing this. So that's a really good sign. Okay. So the other thing I'd like to point out is you can test the model of this digitized errors, this error probability. So if you take, I think this is around 14 qubits. The XEB fidelity is about 22% or so. You then, when you do the simulation, you put in a phase flip, and then which is a pi phase flip in the calculation, in the simulation. And when you look at the cross entropy fidelity, it goes to 0. As I said, if you have a phase flip, it goes to 0. But what you can do in the classical calculation for XEB is to put in a variable amount of phase. And you see, when you do that, the fidelity drops down to 0 and then goes back up again. And this, in fact, completely agrees with the cosine squared of the angle over 2, this formula, well, which is the formula for the digitization of errors. You have an analog error of 1 qubit operation, and you can compute the probability of error from that. And you see this whole idea of digitizing errors, even though it's in the middle of a big calculation, that concept works. Okay. Now you can see here that the circuit errors are a little bit right of the green dots, which is the prediction. And what this means is that the calibration we made for this particular gate, it's one gate out of the few hundred gates of the whole circuit, is a little bit off. And it doesn't affect the end result very much, but you can do measurements of an interior gate and see how well it's working. And this is really nice because with XEB, you can kind of look inside the whole algorithm to see how well it's working. And I think that's a very useful character of this XEB to understand how your circuit is working. At that, I think I'm about at the end of my time, so let me conclude right here and I can answer questions. Just summarizing this, if you build hardware with errors greater than a few %, it's likely that you can do this very sophisticated classical simulation to reproduce those errors. It's a conjecture, but it really tells you you want to build low errors below a few %, where more or less we are now. And I'm going to say errors below about 0.1% for your hardware is where things are really going to start getting interesting and powerful. And I think the quantum supremacy experiment kind of dips its toe into that region. So this is something we need to do. Also point out that you really want to measure your errors and measure your system errors and compare it and error budget it. And there are good tools for doing this now. I talk about XEB, but there's many other tools that people can do that. And then finally, if we want this to be an important and vibrant field in the future, we want to have powerful quantum computers and simulators. And I really want to motivate people to improve their qubits, lower their errors, understand that errors, because that's how we're going to push the field forward and make this an even more important and powerful, field of physics in the future. So I just really want to motivate people to think about this subject as they do experiments, do theory in the future. With that, thank you very much, and I would love to answer questions now.